When you think about a wind turbine, you probably think of something that looks a little bit like this.
But when we think of a wind turbine, we think of something that looks like this.
This is called a Savonius wind turbine.
Savonius turbines usually only use one panel, but our turbine has two to help increase our efficiency.
The two sets of panels are at right angles to each other, allowing the wind to move effortlessly through the turbine. Stop it here, that doesn't sound like wind.
The beauty of the Savonius design is that it can accept wind from all angles.
The goal of any renewable energy product is to produce power, whether due to lack of grid connectivity
or environmental concerns, such as reliance on fossil fuels.
Power is represented by the letter P.
But sometimes engineers get confused about how to calculate P.
So what's the real equation, Sheer?
Well, I'm glad you asked, Sarah. Here's how we calculate it.
Well, first we need to calculate the area, right?
It's easy. For our turbine, we first calculate the length of the blades,
Bing!
and then their diameter in order to calculate the total swept area.
Bing! On our turbine, we calculated the total swept area to be 10.5 square inches, which is 0.00677 square meters.
Using the density of air,
our calculated swept area,
an estimated efficiency of 0.15,
and the velocity in the wind tunnel,
we were able to estimate the power our turbine would generate.
However, the swept area took into account wind coming from all directions.
In our wind tunnel test, the wind was blowing from one direction.
We took this into account by halving the swept area, which halves our total power.
Our final estimation was 0.31 watts.
Upon testing, we measured a generated power of 0.244 watts.
This means our estimation was only off by about 20%.
Sarah, can I get this thing off my hand? Just deal with it, Sheer.